which of course you know how to determine it, right? From previous example, if I give you a point, you can certainly determine the position vector of this point with respect to the center. So here, this is why we have to learn how to calculate mass moment of inertia, products of inertia, because in reality, suppose you devise your objective is to design a component, of course, for mechanical engineering, and this component in a mechanical system is going to spin with respect to axis, a certain axis. And that axis is not necessary to be the principal axis of inertia. That axis is depending on the purpose of this machinery. Therefore, that's why you need to know, suppose I define, I can determine the principal axis of this eraser. Certainly it's XYZ, you can know. But the actual rotation may not necessarily to be along the principal axis, right? You can actually rotate in any way. And when that happens, this is the approach, the equation to show you how do you calculate the angular inertia of any object to an arbitrary axis. Which is why, if you look at this formulation, you need not only the mass moment of inertia, I-axis, I-y-y, I-z-z, even though they are not principal axis of inertia. But you also need to know products of inertia, I-x-y, I-y-z, and I-z-x. So this is why we have to learn how to calculate moments of inertia and products of inertia, because in real world, an arbitrary rotation actually demands the information from both components. Moments of inertia, mass moment of inertia, and mass products of inertia. Okay. Now, let's move on to the next topic, which is three-dimensional equation of motion. And this is the part on my notes, page 67. And in dynamics, in general motion, you already know that we use two major conditions in kinematics. One is a force equilibrium, the other is moment equilibrium, right? This one you must see this so many times. That means the summation of all the forces applied to a system equals to the product of mass times the corresponding linear acceleration in that direction. So you're finding all the forces in x direction, this only correlates to the product of the mass times the linear acceleration in the x direction, and so on and so forth for the y direction and for the z direction. This is what we know for dynamic force equilibrium. This is what we call dynamic force equilibrium. What about moments? For moments, we have this result. If it's moments, then of course, you know that we have to calculate what? You have to calculate, we said that this equals to I corresponding axis, right? Times what? Times angular acceleration, which is alpha I. That's what we said, remember? So these are the two that we talked about before. But they are conditions for the linear or translational motion. Decomposition of a linear acceleration into three components is no problem, because the linear acceleration in the x direction does not bother the linear acceleration in the y direction or in the z direction. So this is always true. You don't have to worry about it, whether there's a coupling. But in angular motion, that's not that simple. For angular motion, you can actually have this object simultaneously spinning in all three different axes. Then the angular acceleration in one direction will be affected by the angular motion in other directions. which is why the general formulation here is what? This is the one I did not mention the first time we introduced this. We've been using this very happily for a while. Now it's the time to show you the reality. The reality is this. It actually has two other components. First, actually, the first term is associated with IY and IZ. So if you call this one I, and of course we're going to define what? We're going to define I, J, K as a substrate. There are three different directions. If you use I as X, and the J and K becomes Y and Z. So here, if we do that, this will become IJ minus IK times omega J times omega K. Now, of course, let's write this down in XYZ so you will not be confused with what is IJK here. Simply is this. Mx equals Ix times alpha X minus IY minus IZ times omega Y times omega Z. So this is the general form. And when you apply to the x-axis, it becomes mx equals Ix times alpha X minus Iy minus Iz times omega Y times omega Z. Now, the other two will be like this. Iy times alpha Y minus Iz minus Ix times of omega Z times omega X. And the last one, Mz equals to Iz times alpha Z minus Ix minus Iy times omega X times omega Y. Now, before we only use this part, which is basically this. Remember? Before we only use this. Before we only use this? Because before, when we consider this kind of planar motion, suppose you consider there's a bar, there's a rod, we have this problem before. Right? And there's a piston, so you actually move in this way. We said when this objects move in the linear direction, either directions, and what will be the angular motion of other components? Like this one is going to move this way, so it's going to go like this. This one is going to go like this, right? When we study these kind of examples, the angular motion we consider here means there's only one angular component from the angular motion, which means that in this kind of problems, we constrain our discussion on only a single direction, which means we did not consider that this object could actually also rotate in the perpendicular directions because we did consider only a two-dimensional problem. In two-dimensional problems, the direction for the angular components will always be perpendicular to the plane, right? The angular component, like suppose I want to talk about this moment. I said there's a moment, and moment equals to I times alpha I. So this is the moment, which is, of course, you can picture that. What is a moment like this? Suppose I want to bend. I have a hinge here, and suppose I provide a force. That, of course, can be easily imagined, right? There's a beam oriented in this direction, and I'm going to apply the force at this end. So it's going to create this kind of moment because after applying the force, this whole thing is going to rotate like this. That makes sense? Right? So this, of course, the force will produce equivalent moment, which will result in this kind of motion associated with the mass moment of inertia times the corresponding angular acceleration. Now, what is the direction of this alpha?